Welcome back, everyone. Today, we're going to talk about one of my favorite topics, the Tate module, which is named after John Tate, who passed away actually recently. He was a great mathematician, but also a really, really nice person that I got to meet a couple times. Anyway, previously we've done in the class, we did a quick introduction to algebraic geometry up to the Riemann-Roch theorem. So we could define elliptic curves, we can define what genus is, and then we used Riemann-Roch to give Weierstrass models of elliptic curves. And then we also used what we learned about divisors to construct or to endow elliptic curves with a group law that we could define geometrically, but then actually through the group law, through the divisor group, the Picard group, we gave a proof of the associativity, for example, of the group law. Then the last few lectures, I talked about isogenies of elliptic curves and the dual isogeny. And those will come back to prove a few more things. So we're going to go ahead and start with the Tate module, though first I want to remind you something we did last time. So as a consequence of isogenies, in particular, multiplication by M map, the multiplication by M map is an isogeny. So M from E to E that sends P to the sum of P copies of M copies of P, that is an isogeny, and we use the theory of isogenies and dual isogenies to actually prove that the M torsion, so this is called the M torsion subgroup of E, those points that are of order dividing M, so M times P is 0, but if the order is dividing M, then those are also in the M torsion. That is isomorphic to two copies of Z mod M. Okay, in characteristic 0. If the characteristic is P and you're looking at the P torsion, then it can be that the P torsion is either trivial or one copy of Z mod P. Okay, so for example, and this is part of a homework problem of what I call the homework set number 2. When you have an elliptic curve over Q or over another field characteristic 0, and you give your elliptic curve in Weierstrass form, in sort of short Weierstrass form, or just y squared equals f of x with f of x a cubic. If you look at the 3 roots, then the 2 torsion is very easy to actually write down. And this is for you to prove that the points of order 2 are precisely the points O, the point at infinity, which is of order 1. And then the points of actually order 2 are A0, B0, and C0. Okay. And then you can actually add those points and check that those laws are satisfied, that every point P, Q, and R is exact order 2. So you can actually prove by hand that the 2 torsion is isomorphic to 2 copies of Z mod 2. Okay, not necessarily defined over Q. So those points, if f of x is an irreducible polynomial, then those points will be actually defined over Q bar, not over Q. But for example, you can take elliptic curves such as this one, which has come up before. The polynomial in X is, it factors completely, and then you can give the coordinates of all the 2 torsion points are in Q. So the full 2 torsion subgroup is defined over Q. This turns out we will show, we're going to talk about the Tate module, then we'll talk about the Weil pairing, and then show that this is actually, if the M torsion is defined over Q, actually M is 1 or 2. It cannot happen that you can have a 3 torsion fully defined over Q. For example, to have the 3 torsion defined over a number field, the number field has to contain the third roots of unity if you wanted the 3 torsion. If you want the M torsion, actually the mth roots of unity have to be in the base field. And we will show that in a moment. So to talk about the Tate module today, first, if you've never seen inverse limits, then I need to give you a quick crash course on inverse limits. So we're going to do that. So here's what an inverse limit is. It's a construction which is it's like a group theory construction. So I'm going to start with a sequence of groups. And it comes equipped with a sequence of maps also. From one to the previous group in the sequence. Okay. And so we have a chain, we have G0, and then there is through F1, G1 is connected to G0, and G2, and G3, and so on. And so this is F2, F3, and so on. And the inverse limit of that chain of Gn Fn, typically just we just read inverse limit of just Gn, and the Fn's, the maps, the connecting maps are understood, or we say with respect to the maps, so on, is a subgroup of the product of all groups from 0 to infinity, which is given by sequences that are coherent. So there are infinite sequences of elements in each one in one of the groups, such that via the maps, each one goes to the previous element. So if I have Fn and apply it to Gn, I should get Gn minus 1. Okay, so these are called sometimes coherent sequences with respect to the maps Fn. Okay. Let me start with an example of something you've seen maybe as far as calculus, basically. So this is one of those exaggerations mathematicians say. So we're going to construct power series in this way. So I'm going to take my GNs to be integers modulo powers of x. Okay, so that is a group under addition, right? And then my maps, my Fn from polynomial rings modulo the nth power of x down to polynomial rings modulo the n minus 1th power of x. Let's just send a polynomial, maybe not f, since f is already taken. Let's call this g of x modulo x to the n. Let's just send it to gx modulo x to the n minus 1. Okay, then what is the inverse limit of these groups? So this is going to be sequences of polynomials. So there's going to be, let's start here with n equals 1. So there's going to be a polynomial g1x, a polynomial g2x, a polynomial g3x, etc., such that so each gn of x is a polynomial, an integer polynomial, and such that when you reduce one modulo a higher power of x or a smaller power of x, then you get the previous one, such that gnx is congruent to gn minus 1x modulo x to the n minus 1. So basically what this is saying is that this is a polynomial modulo x, but a polynomial modulo x is just a constant term. This polynomial is a polynomial modulo x squared, such that when I reduce the modulo x, I get G1. So the first coordinate gives me the constant coefficient. The second term, I can think about it. So this is just, say, A. This is going to be essentially a plus bx, because it's modulo x squared. And the coefficient A is the coefficient from G1. For this one, this is modulo x cubed, so it's going to be something like A plus bx plus cx squared, and that's all the information that I really need from that term, and so on. But you see in the limit, I'm adding more terms and more terms and more terms, so I'm actually getting that this is some sort of like a series of AI's x to the AI for, writing too long. AI xi for I bigger or equal to 1, say, or 0. Okay. Right. So so basically what this construction is just defining power series in a slightly bizarre way, but it's just a power series with integer coefficients. Okay. All right, so let's do something a little bit more of number theory interest. So another construction. Did I call it example 0? Yes. So this is going to be example 1. In example 1, we are going to give my first group is just going to be 0. My first group is going to be z mod pz. Here p is a prime. And G2 is going to be z mod p squared z, and so on, so that Gn is z mod p to the nz. And then I need maps, and I can do, just like in the polynomial case, I can actually define just a reduction, so that I go from z mod p to the nz to z mod p to the n minus 1z. I can take a number modulo p to the n and send it to the same number modulo p to the n minus 1. Reduction modulo p to the n minus 1. And then I can do the inverse limit of my groups, Gn. This is the inverse limit of z mod p to the nz, and this is what's called the p-adic integers. And they are nothing other than, in this notation, there's other ways to express p-adic integers, but I actually like it. I like working with them in this notation, that they are just, well, if you, the first coefficient is just 0, so I can actually forget about that. They are just sequences, A1, A2, A3, etc., such that an is congruent to an minus 1 modulo p to the n minus 1. Okay, so integers that are congruent, and each number gives you a higher congruence condition. They are coherent. Okay, so this is the condition modulo p, the condition modulo p squared, condition modulo p cubed, but they have to be congruent. So for example, if p is 5, here is a p-adic integer. I'm going to call it u. I can write 3, 8, 8, 133, 133, 3,258, etc. is the beginning of a p-adic expansion, of a 5-adic expansion, because this is the This is the condition modulo 5. This is the condition modulo 25. And you see that 8 and 3 are congruent modulo 5. So if I reduce 8 modulo 5, I get 3. So those are, that works. This is the condition modulo 5 cube, 125. It just says that if I reduce 8 modulo 25, I should get 8. And that's true. This is the condition modulo 625, and 133 is congruent to 8 modulo 125, and so on. Okay, this is just some random number that I picked, but that is the beginning of a p-adic expansion, of a 5-adic expansion. By the way, these ZB is a group under addition, and it's in fact a ring. I can add and multiply, so the ZP is a ring under coordinate-wise addition and multiplication, because those at each coordinate that is inherited from the fact that Z mod P to the NZ is a ring. Okay, so I can add and multiply numbers. All right. So now let me give you another example, even a little bit more complicated, or just more number theoretic, or algebraic number theoretic, algebro number theoretic. So again, let P be a prime, and let mu Pn is the P to the nth roots of unity, which is a group under multiplication, right? So this is, you can think about them as e to the 2 pi I, e2 pi I m over P to the n for m. Like this, if you're thinking of Q bar as inside the complex numbers, then you can think about them like that, as those complex numbers. Okay, and I need a map, a connecting map between the P to the nth roots of unity and the P to the n minus 1th roots of unity. And one easy map is that I can take root of unity zeta, I can raise it to the pth power. If I raise it to the pth power, then if it was a P to the nth root of unity, now it's a P to the n minus 1th root of unity. So that gives me a map between the two, and I can define, so I can define the inverse limit of the mu's like before, and now these are going to be coherent sequences of roots of unity, each one of a higher P to the nth power, such that when I raise to the pth power, I get the previous root of unity. Okay, so so these are sequences each one like that, and if I raise 1 to the pth power, I get the previous one. Okay, so coherent sequences of roots of unity of p power order. Perfect. So this is actually called, this is the first example of what we call a Tate module. So this is usually called TP mu, and is the Tate module of Q. Okay, and this is actually this is a group itself under multiplication, coordinate-wise multiplication. We don't have an addition here. You add 2 roots of unity, it doesn't have to be a root of unity. So the Tate module is a group under multiplication, And it is also, why is it called a module? Well, there's got to be some module structure. It is also is a ZP module. Okay, so let me show you the action of ZP on roots of unity. So let U be a p-adic integer. So U is U1, U2, etc. A sequence of integers that are congruent. Okay, so again, these are integers such that UN is congruent to UN minus 1 modulo p to the n minus 1, right? And now let something in the Tate module, or what are we going to call it? Let's call it T for Tate module. So this is going to be an element of the Tate module for Q. T is going to be a sequence of roots of unity. So these are each one and a root of unity such that when I raise to the pth power, I get the previous one. Okay, so now how do I define U times T? How does ZP act on that? Well, it's just going to send, I'm going to raise each root of unity to the power of U. So it's going to be 0, 1 to the U1, 0, 2 to the U2, 0, n to the UN. All I have to show you now is that this is actually well defined in that I get another element from the Tate module. So now what I need to know is what happens if I take this person here. If I raise it to the pth power, I should get the previous element in here. So, well, this is, I can raise this to the pth power instead. Those powers commute, and I get that I know that is the condition here that gives me the previous one to the nth power. But now the n minus 1th root of unity, those exponents, they actually work modulo p to the n minus 1, right? Because if I have, say, if I have a 5th root of unity, zeta to the 3 and zeta to the 8, they have to give me the same number because they differ by zeta to the 5, which is 1, if zeta is a 5th root of unity. So it turns out that this is the same as zeta n minus 1, and the exponent I can always reduce modulo p to the n minus 1, but that is precisely by the condition above that is congruent to un minus 1, which is the previous element in my sequence as defined. So that works. Okay. So what we've seen is that the Tate module is a ZP module. Okay, and it's a ZP module of rank 1.
Sorry, so just to confirm, we go from those last two steps from zeta n minus 1 u to the n to zeta n minus 1 u to the n minus 1, because we know that we're allowed to congruently chop off the p to the n component when this is a p to the n root of unity.
Yeah, because, well, I mean, here's another way to see this is that, and this is going to come into what I was about to say, is that what are the p to the nth roots of unity? Like in here, you see here, it doesn't matter. Here, m only matters modulo p to the n, right? If I change e to the 2 pi I m plus p to the n over p to the n, this is going to be e to the 2 pi I m p to the n times e to the 2 pi I, and the p to the n and p to the n cancel, so I get e to the 2 pi I, which is 1. So this is just e to the 2 pi I m modulo p to the n. So m is actually just, it just matters modulo p to the n. What that says is that the p to the n roots of unity are actually these are isomorphic as a group to z mod p to the n z. Okay, so when you raise exponents, and that isomorphism comes from you take one root, and then if you raise two powers, then you go through all of the p to the nth roots of unity, and the powers that you get there are those powers m, and that is the corresponding z mod p to the n z number. Okay, so so basically what this says also is that if zeta is in the p to the nth root of unity, and a and b are congruent modulo p to the n, then zeta to the a is congruent, it's equal to zeta to the b. Okay, and that that gives you that that equality here that we needed. Okay, so so also because so t p mu is the inverse limit of the mu p to the n, this is isomorphic to the inverse limit of z mod p to the n z, which is the p-adic integers. So it is zp modulo of rank 1. Okay, but when you sort of like hide everything, is isomorphism, sort of like the action of zp on roots of unity is sort of like hidden away. So it's nice to see it like I did here, like what zp actually does to an element of the Tate module. Okay, so now finally we're able to construct the Tate module of an elliptic curve. So now, what example was that? Example 3. So now example 3 here is going to be the following. So now let E over K be an elliptic curve. I'm going to assume here that the characteristic is 0, but that doesn't matter, except that once I do isomorphisms, then it's going to matter. P is prime. P is a prime, and then our groups Gn are going to be the p to the n torsion subgroups of E. By the way, the if you go back to the previous slide, this right here, the p to the nth roots of unity are precisely the p to the nth torsion of Q bar. Okay, so if raising to the p's power was my my isogeny on Q bar, so I could let me perhaps put a remark here. If I defined multiplication by m on Q bar star such that it sends something in here to the mth power, then what is the p to the nth roots of unity are precisely the kernel of this multiplication by p to the n. right? The numbers that when I raise to the p to the nth power give me 1. So similarly, e p to the n, this is the kernel of multiplication by p to the n. Okay, so this is my subgroups are the p to the n torsion, and I need maps, connecting maps from the p to the n torsion to the p to the n minus 1 torsion, and that I can just do like I did with the roots of unity. I'm just going to multiply by p. If I have a point of order p to the n, if I multiply by p, the image is a point of order p to the n minus 1, right? Or of order dividing p to the n, when I multiply by p, then now the order is at most p to the n minus 1. Okay, and then we define the limit, the inverse limit of these groups of torsion. That is what we call the Tate module of the elliptic curve. Or the p-adic Tate module of E to refer to the fact that we're doing it for P. Okay. Now, note, why am I calling it the p-adic Tate module is because recall that because of the characteristic is 0, what we said previously is that the p torsion, the p to the n torsion is isomorphic to 2 copies of z mod p n. And therefore, when I compute the Tate module, it's going to be the inverse limit of the p to the n torsion is going to be the inverse limit of 2 copies of z mod p to the n z, which is going to give me, each one of the copies is going to give me 1 copy of the p-adic. So this is zp plus zp. Okay, so it's a rank 2 p-adic module. Okay. Great. The multiplication, by the way, is like the action of ZP on the Tate module is similar to what we saw. So if I have an integer, a p-adic integer u. Okay. Let's call it u1, u2, etc. un in ZP, and I have an element of the Tate module. An element of the Tate module is going to be a sequence of points, P1, P2, let's call them Qs, Q1, Q2, etc., Qn. Then U times T is just going to be U1 times Q1, U2 times Q2, UN times Qn, etc. And you can check that because I shouldn't have closed this parenthesis too soon. It's an infinite sequence. You can check that because Qn times P has to be the previous point. That implies that UN Qn times P, this is also UN minus 1 Qn minus 1. Okay, and that is because multiplication by P commutes with multiplication by UN. So first you can say P times Qn is UN minus 1, and then Qn minus 1 is a point of order P to the n minus 1 at most. So what you multiply with is going to run modulo P to the n minus 1. So UN is congruent to UN minus 1, and those two things are equal. Okay, and makes the action well defined. So that's the action of ZP on the Tate module of an elliptic curve. Okay, so this is a way of very neatly packing all the information about points of order P, of P-powered torsion points. And it turns out that, surprisingly, sometimes you want to know something about P torsion or about your elliptic curve, and you don't care so much about the P squared torsion or P cubed torsion. But we're going to see that by putting everything together, you can actually get information about the entire Tate module, and then reduce modulo P and get back information about the P torsion that you cared about. So that's some surprising feature, that you can get information about the entire P tower to get back to information about the P torsion itself. All right, so let me now now the other feature that these Tate modules have is that they have a Galois action on them. At least the Tate modules have a Galois action on them that gives this extra structure. The Tate module enjoys a Galois action. So, for example, in example 2, the Tate module of Q remember, for roots of unity, we have that the absolute Galois group of Q, which is automorphisms, field automorphisms of Q bar, which fix Q, that group acts on roots of unity. If you act with Galois on a root of unity, that's an algebraic number, so it has to send a root of unity of order P to the n to another root of unity of order P to the n, or dividing P to the n. So it acts there. We write this, I'm going to abbreviate by GQ, and we say that there is an action. We write this to denote that there is an action of Galois on it. And moreover, and the action of Galois commutes with the connecting maps Fn, which in this case, remember, they were just raised to the pth power. They commute because, well, if sigma is an automorphism, is a field automorphism, so it behaves well with algebraic operations. So if sigma is there, then what is Fn of sigma of a root of unity, of a P to the nth root of unity? That is going to be, the action of Fn is just raised to the pth power, but raising to the pth powers commutes with field automorphism, so that is sigma of that root of unity to the pth power, and raising to the pth power is what Fn does. So this is sigma of Fn of zeta. So you see Fn and sigma have commuted. This allows to define a Galois action on the entire Tate module, to extend the Galois action to all of the Tate module of Q by simply saying that sigma acting on a sequence, whoa, bad zeta. So if I have an element of the Tate module, I'm just going to act coordinate-wise with my Galois automorphism. Okay, and by the line above, this is well defined, and my new sequence is also an element of the Tate module. Okay, all right. Moreover, now since the Tate module we said is actually just one copy, is isomorphic to one copy of ZP, is a rank one ZP module, then we know how to compute the automorphisms of that module. They're just going to be multiplication by a unit. So the automorphisms are ZP cross, so the units in ZP, which are things that are non-zero modulo P, any non-zero element modulo P. So as long as the very first coordinate is non-zero modulo P, that is going to be a unit. You can work that out and see that that is an invertible element in ZP. And this induces what we call our very first example of a Galois representation. Induces a Galois representation. So it is a homomorphism. I'm going to call it chi P from the absolute Galois group to automorphisms of TP of the Tate module of Q, which once I choose a basis of my Tate module, ZP basis, that is going to be isomorphic to ZP cross. Okay. And that just tells you how every sigma is going to act as one automorphism. That automorphism corresponds to one p-adic unit, and that tells you how to what the image of that chi p is. This is called the p-adic cyclotomic character. And what is the image? The image is sigma goes to a p-adic unit. I'm going to call it a sequence of UNs, integers, UNs, such that how is that UN determined at every coordinate modulo P to the n? The determination is if I take if zeta is P to the nth root of unity, then sigma of zeta has to be a power of zeta, of zeta, and then that power is actually UN. Okay, so the nth coordinate is the unique integer modulo P to the n. It's not unique integer, it's an integer modulo P to the n, such that zeta goes to zeta to that number via sigma. Okay. This, by the way, sometimes we can, so we have a p-adic Galois representation to ZP cross, and that tells you the entire action on all the P to the nth roots of unity. But you can reduce modulo P, for example, and then what you get is modulo P is just forget about the entire p-adic expansion. Just remember the first coefficient, U1. Okay, so here sigma goes to UN, and this just sends this to U1 mod P. And again, what that says, this map now, let's call it chi P bar that goes from the Galois group to Z mod PZ cross. This is the mod P cyclotomic character. And it is defined, again, if this is a non-trivial pth root of unity, and it doesn't matter which one you pick, they all send to the same power, then it is defined by sigma goes to U1 mod P, such that sigma acts on the zeta root of unity. It has to be sent to a power of zeta, and the power is U1. Okay. The fact that it has to be a power of zeta is some fact in algebraic number theory, which is that the fact is that the Galois group of the field generated by p to the nth roots of unity is actually z mod p to the n z cross. And all the automorphisms of the Galois group are induced by what power goes to what power a root of unity is sent to. So if we have an A mod p to the n here, this is sent to the automorphisms that sends zeta to the A. That is an isomorphism of groups of the Galois group. Okay. Right, so that's a lot about the cyclotomic character and the action of Galois on roots of unity. And now we're going to do exactly the same thing, but for the Tate module. So now, in example 3, we had constructed the Tate module. So now we had E over K. Page fell. This is an elliptic curve, and we had a prime P, and then we had constructed the inverse limit of the p to the n torsion subgroups, called it the Tate module of E, and this was, remember, isomorphic to 2 copies of ZP. Okay, so now there is an action of Galois here too. So it turns out that Galois, here it would be K bar. This is true if the characteristic of K is 0. Now the Galois group, the absolute Galois group of K acts on P torsion, on the P to the n torsion. Why would that be? So let's see if Q is P to the n, and sigma is an element of the absolute Galois group. Let's see what happens with sigma of Q. Well, I'm hoping that that is a p to the nth torsion point also, so it has to be killed by p to the n. So let's see what happens. Now, So the p to the n map, the p to the n multiplication by p to the n is defined over k. So here, what I'm going to use is that p to the n is an isogeny defined over k. And what that means is that it's given by polynomials that are defined by defined over k. Every coefficient of those polynomials defined over k. Those are going to be very complicated polynomials with a very complicated map in terms of like the polynomials that appear there, but they are defined over k. And if you have p to the n applied to sigma q, so it's just sigma q is there's x, y coordinates, and now sigma has acted on the x and on the y, right? And then I apply p to the nth to that. The sigma can come out of everything because it's a field automorphism that fixes k. So what happens here then is that the sigma can come out of the multiplication. Okay, so there's two things here. One thing is that sigma q is sigma acting on whatever coordinates those are. That is sigma of x naught, sigma of y naught. Okay, and then when I apply a function, so if f, say, if g of x, y has k coefficients, then g of sigma x, sigma y is the same as sigma applied to all of g x, y. Because the coefficients of g, which are in k, are fixed by sigma. So, so if that is a rational function, then the sigma commutes with the g. Okay. But now, since q is a p to the n torsion point, this has to be 0, O, and sigma of O, it just sends, those are actually defining k is 0, 1, 0, that goes to O. So sigma q is also a p to the n torsion point. Okay. And moreover, the fact that it commutes with the p to the n map, it allows me to extend the action to all of the Tate module. And so the Galois group of K acts on the entire Tate module, and since the Tate module is 2 copies of Z mod PZ, then what I get now is a Galois representation, which we are going to call now rho of EP, that goes from the absolute Galois group of K to the automorphisms of the Tate module. It sends sigma to the automorphism that sends a sequence Qn to the sequence sigma of Qn in the Tate module. And the Tate module is isomorphic to 2 copies of ZP. So the automorphism group is actually isomorphic to GL2 with coefficients in ZP. Okay, this is non-canonical. I need a basis. There's a choice of basis here. This I'm going to write in red. Okay, that matters, but it only matters up to conjugation. So what that says is the image of this representation is well defined up to conjugation. If I pick another basis, what that's going to do is going to conjugate the entire image So the image can be, if I have one subgroup as an image, I conjugate, and that's picking another basis, and that will give me another image, but they're just conjugates of each other inside GL2 of ZP. Okay. Yeah. Now, a fact that we will see later is that the determinant. So if you have a representation to GL2 ZP is a representation from this Galois group to GL2 of the p-adics, the determinant will give me some map down to ZP cross. Okay, so I can compose. Let me go from GK to GL2. I'm going to go there via row EP, and then I'm going to take the determinant. That's another group homomorphism. That's going to send me to the determinants. The possible determinants are units in ZP, and this map turns out that from here to here is going to be chi P, the cyclotomic character. Okay, so that's nice that that determinant, that map from the Galois group to ZP cross is something that we know. It's the cyclotomic character. Okay. All right. Very good. So what is the Tate module good for? Let me give you a bunch of results about the Tate module, just to show that, well, it's good for something. So for example, the Tate module can be used to study isogenies. So if you have two elliptic curves, E1 and E2, then if you have an isogeny from E1 to E2, then this induces an isogeny, or it induces a map between P to the n torsion and P to the n torsion. This it induces, it's the restriction to the P to the n torsion, and it induces a ZP linear map between Tate modules. Okay. So it turns out that there is then a map between homomorphisms between E1 and E2 to the HOMs between Tate modules. Okay, and it turns out there's a theorem. I think it's theorem 7.4 in the book, that this map, so the natural map, sure, the natural map between, if we tensor the HOMs from E1 to E2 by ZP to the HOMs between Tate modules, that sends an isogeny to the isogeny that I described before between Tate modules. This map is injective. Okay. The proof is long, so I'm not going to do that proof, but I'm going to use this to show something else, which is the following. So a corollary of this is that the homomorphisms from E1 to E2, so isogenies, is a free Z module of rank at most 4. Okay, so here's the proof of this fact, is that first we saw that before, actually also using isogenies, that HOMS from E1 to E2 is torsion-free Z module. And then we can, if you want to compute the rank of the rank over Z of this Z module, that's going to be the same that if I compute the rank over the ZP of the module. Okay, this would only change if somehow I was killing some torsion by doing the tensoring with ZP, but there's no torsion to be killed because HOM is already torsion free. And by theorem 7.4, the rank of the ZP module HOM E1 E2 tensor with ZP is less or equal to the rank over ZP of the HOMs of TP1 and TP2. Okay. But now choosing bases, if I choose bases for the Tate modules, remember the Tate modules are ZP cross ZP, or ZP plus ZP, 2 copies of ZP, then the HOMs is just like, where do I send the first generator of a ZP and where they send the second generator of a ZP, that is the isomorphism of TPE1. So the map just gives me a matrix, a 2x2 matrix will define each one of those HOMs. So these are actually just, I need to know matrices. To define one, I need to give you a matrix, 2x2 matrix over ZP. And this is of rank 4. And that proves the corollary, because then the rank of HOM over Z is less or equal to the rank over ZP of the HOMs of the Tate modules, and that is at most of rank 4. Okay, so there you go. Now, let me.
Sorry, can I ask a?
Yeah.
I'm so sorry to back up a little ways here.
Yeah.
I might be missing something obvious. How do we define the ZP linear map phi of P from TPE1 to TPE2? Is that like? I'm sure that's a natural map, but
Yeah.
I don't understand what natural means in this context.
Yeah. So we are just taking, here the map is exactly the same at the level of P to the n torsion. Phi of Q is whatever the isogeny is, right? So I don't even know what you write here, other than just it does exactly what phi does. So it just sends to phi of Q. Phi is an isogeny, so it's a group homomorphism. So it sends P to the n torsion elements to P to the n torsion elements of order dividing P to the n to elements of order dividing P to the n. It might drop in order in some cases, okay, but it's in there. And then the map here would send a sequence to a sequence of phi's, just like that. Okay, and now you can check that the compatibility will also hold. That if the QNs are compatible, phi will actually commute with multiplication by P and then you have that that if I multiply by p, then because phi is an isogeny, is phi of qn added p times, and that is phi of qn added p times in quantity.
Okay, awesome.
Does
That
make
makes sense.
sense?
Thank you. Yep.
Yeah, so it's that map, and that gives you the isogeny between Tate modules. And then you can check that actually that will be a ZP linear, that if you multiply QNs by a p-adic unit, the p-adic units, again, because they coordinate by coordinate are integers and phi is an isogeny, those integers will come out and will act on the result. Okay. All right. So I have a few minutes. So let me just give you a few, like some of the greatest hits and on the theory of Tate modules. And these are some like fairly deep results. This is theorem 7.7. And again, these are fairly deep results that there is, first of all, there's a map, HOM, so defined over K. So we did HOMs in general, but if you actually want HOMs that are defined over K over the base field where the ellipticals are defined, we do get a map to HOMs defined over K of Tate modules. But now over the base field, this is quite tricky to show that this is in fact an isomorphism. We just, in the book, you can find the proof that this is injective, but isn't actually an isomorphism in two cases. A, if K is a finite field, this was actually proved by Tate himself. And B, and this is quite deep, in the case of number fields, this was proved by not Deligne, Foltings. Okay. Now another deep theorem is something called what we call Serre's open image theorem. And is the following, that so let K be a number field, and E over K, an elliptic curve, without complex multiplication. So remember that what that means is that the endomorphisms of the elliptic curve are actually just Z. There is no extra endomorphisms. The only endomorphisms are multiplication by M maps. Then it turns out that, remember, we have Galois representation, rho EP from GK to GL2 ZP, and you wonder how big is that image. So it turns out that rho EP of GK, the image of that representation, is of finite index. And in GL2, so quite large. If it's finite index, GL2 of ZP is pretty big. So it is a finite index in GL2 ZP for all primes. You have one for each prime, and it turns out it is for a finite index for all primes. And in fact, it is all of it. Is all of GL2 ZP for almost all primes, for all but finitely many primes P. Okay. You can see here that we have there is no CM. In the case of CM, the image is actually quite different. I'm not going to write it down, but it's quite much smaller than GL2. ZP is essentially dihedral, so it's almost abelian. So there's a small extension of K, where if you go up that extension, then you have a abelian image. This is the whole theory of complex multiplication is beautiful, but is one of the topics and the advanced topics of elliptic curves of Silverman's second volume. So the image in the complex multiplication case can be very nicely understood, and it is very nicely understood what it is, but you do not get anywhere close to all of GL2 of ZP. And then the last theorem I wanted to mention is a much more recent result by Jeremy Rouse. By the way, Jeremy Rouse is speaking tomorrow in the algebra seminar. So I would really recommend that you attend that talk. And David Zurich Brown have given a complete classification, give a complete classification of two-adic images, so of the case p equals to 2. So what this means is that there are, up to conjugation, exactly 1,208 possibilities for the possibilities of the two-adic image of the Galois representation over Q. Okay, this is a complete classification of the case. P equals 2 for K equals Q when there is no CM. And then I showed that in the case of CM, there is another 32 possibilities up to conjugation. And that gives you a complete classification of what are the two-adic Galois representations that come from elliptic curves over Q, which is quite interesting that we have that. And there's Rouse, Zurich Brown, and others are working on trying to come up with a classification of the three-adic images of Galois representations and so on. Why do we care about Galois representations? Is because two reasons. One, they give you all sorts of information about the structure of the elliptic curve, of the torsion subgroup of elliptic curves. And second, they give you information about the absolute Galois group. One can say that actually algebraic number theory or number theory is the study of the absolute Galois group of Q. And these Galois representations give you very large chunks of that. So, for example, here is telling you that for every elliptic curve, you have some representation, and the representation, you know, if it's a group homomorphism, what this is telling me that is the absolute Galois group modulo the kernel of that is isomorphic to GL2ZP. So it's giving you very large chunks of the absolute Galois group, constructed in a way that we know how everything works. It works by how the action of Galois works on some geometric object. So it's a very nice interpretation of the absolute Galois group over a chunk of the absolute Galois group in terms of geometry. And we, in fact, there are some conjectures that say that essentially all such Galois representations come from geometry in one way or another. There is some arithmetic geometric object where Galois is acting, and that representation actually comes from there. And whenever you can construct a Galois representation that looks interesting and has all the nice properties, it seems they come from geometry. So this is one such instance of those representations showing up in nature, quote unquote. All right, so that's all I wanted to say about the Tate module, and then next time we will cover the Vey pairing, which made already an appearance today, and we will prove a couple of other properties of these representations. Okay, so I'm going to stop there.